Hi everyone and welcome to a new video about parameter estimation. This is our example about a mechanical system, and in this example we will try to estimate the parameters of the damping coefficient, the spring constant and the value of the mass of a mass damper spring system. Of course we will do the calculations step by step and also work out the simulations and verify our calculations in MATLAB. So this is our example. We have the response given of a system. This is for a step input, which is a force, and it has a value of 4 newtons. So you apply here a force of 4 newtons at time equals to 0. And then you measure or you determine the response, which is given by x here, and this is the response. That's what you actually will get. So we have the damping coefficient here, which is of course a damper. We have the spring here, which has its own spring constant, and we have the mass. So these three are here shown. So we have the system. This is a mechanical system with the damper, spring, and a mass. Okay, what we want is to determine the values of the mass, the damping coefficient, and also the spring constant. So we have 3 unknowns given this response and also the input, which is a step input with a value of 4 newtons. So how do we start? Let's look at the solutions step by step. Now for this mechanical system we can set up the differential equation using the Newton's second law. So Newton's second law says the following: the mass has an acceleration, so the mass times the acceleration of that mass will be equal to the forces which will be applied on that mass. So we have the force which is then in the positive x direction, which is the F. And these two forces, which will the damping force and also the spring force, will of course counteract that movement in the positive x direction, so in the right direction, and you will have 2 counteracting forces in the left direction. So what we have is then the following differential equation form. So we have the mass times its acceleration plus the damping force, which is actually the damping coefficient and also the velocity of that mass, plus the spring constant and also the movement of that mass. So times that mass movement is equal to the applied force F. So this is from the Newton's second law. If I now convert this to the Laplace transform, and then assuming of course the initial conditions are all 0, you will just substitute for the differential an s. So if you have a second derivative, you will have of course an s squared, and all the parameters will be a capital letters. So we will have also capital letter F and also the capital letter x. So this is the change from the time domain to the frequency domain or the Laplace domain in this form. Now we can of course then rewrite this in this form such that we have the x of s here, and then we have isolated that and we have the parameters here in one bracket, and this is then the response of course or the input f. Okay, the system transfer function can now be determined easily by looking at this expression. We can then say the x is our response and input is our force, which is f. Then we can say g is equal to the output divided by the input, which is the 1 over ms squared plus bs plus k. We can rewrite this by dividing the numerator and denominator by m. Then we have the 1 over m over s squared plus b over m times s plus k over m, which is sometimes easier to work with. Okay, that's just the system transfer function using the differential equation, and so from there the Laplace transform. Of course we need a model to determine the values for the spring constant, the damping coefficient, also the mass. So the system model for this one is required. Now if I look at this system, it is a system without any zeros or any delay. So it is a second order system. You can see actually that is also starting with a slope of 0. Of course it can be a third order system, it can be a fourth order system, but let's assume for simplicity that this is a second order system. So for the second order system we have this system model which has 3 parameters, which is the DC gain, or the steady state gain, which is given by this KDC. It has a natural radian frequency given by omega sub n, and also the damping ratio, which is something else than damping coefficient, which is zeta. So these three will be determined from this plot, and then we will use this transfer function also to work out the values for the damping coefficient, the mass, and also the spring constant. Okay, what are the observations from the graph? So let's look at the observation from the graph now. Just looking at the output, we can see the shape of the curve, as we discussed earlier, is close to the second order system. It is definitely not a first order system. It can be, of course, a third order system again, or a fourth order, or maybe a higher order system. But for simplicity, we can assume, and that will do the job very nicely for second order system. Why is this definitely also a second order system? Because we have mass and damper and also the spring constant, and we have already determined the differential equation for that one. Of course, these are linear equations, so we assume that the damping coefficient is given by this expression, and also the spring constant is given by this expression. Of course, if you make it a little bit complicated, you can of course also have a little bit complicated system. So assuming that this is a second order system, we can move on with our calculations. Okay, what you see is also the value, or the steady state value, the final value of this line will approach a value of 6 centimeters or 0.06 meters. So the steady state value, or given in this symbol, is then 0.06 meters. What you also see is that there's a peak value of 8.1 centimeters, and it is then at 0.32 seconds. So I have then two data points, which is actually the peak time, which is then 0.32 seconds, and I also have the peak value, or the X max, which is then 0.081 meters or 8.1 centimeters. So those are important. Important data points for us to determine the values for this system. Okay, what are now the parameters? Let's first look at the DC gain, or KDC. KDC is actually given by the output steady state value divided by the input steady state value. Now the output steady state value was 0.06 meters, and input is just 4 newtons. So we have now 0.06 meters over 4, so we have 0.015 as the DC gain. Okay, that's the value for the DC gain, and the units for this DC gain of course is meters per newtons. What you also have is the overshoot from this plot. So you can see that the overshoot, which is given by m sub p, is equal to the peak value minus the steady state value over that steady state value. So you actually determine the difference between the peak and the steady state value over that steady state value. If you substitute the values we have found here and then calculate this, you will get 0.35 for the MP. That is in percentages 35, so 35% overshoot for the system. Of course, we want to have the damping ratio using this model. So if you use a formula to determine the damping ratio from the overshoot, you can use this formula, substitute the value for the MP, you will get 0.317 for our damping ratio. So we already have two of the three parameters for this second order system model. The next one is the natural radian frequency, omega sub n. Now omega sub n has a relationship with the peak time. We already have that, and that's shown here. Omega sub n is equal to pi over that peak time times the square root of minus 1 minus the zeta squared. We have determined the zeta already. We know the peak time from the plot, so we can substitute the values. We'll get 10.35 radians per second. So we have now the necessary parameters of this second order system model. So let's move on. So system model for our second order system was this one, and these are the values again to repeat what we have determined. Now we will now compare the parameters here, the terms in the second order system model with what we have in our system. So g of s was determined from the differential equation as this one, and if I now compare the results, I can see that the kdc times omega n squared must be 1 over m. That's actually just the numerator of the value here, which is the h, is equal to the numerator of the g. That's what we have here. So if I now rewrite this, I can say m is equal to 1 over that, so 1 over kdc times omega n squared. I have the values, so I can just substitute what I have, and I will have 0.622 kilograms. So 622 grams. So it's actually for the mass. So we have one unknown already determined. So the next one is again looking at the terms. So 2 times the zeta times the omega sub n must be b over m. That's shown here. This is the next one. So the b, which is then the second one, the damping coefficient, will be then a 2 times zeta times omega sub n times m. If I now again substitute the values, the damping ratio, the omega sub n, the natural radiant frequency, and also the mass we just determined, I will get 4.08 newtons per meter per second. That's what I have for my damping coefficient. So the final one is the spring constant. Again, I look at this one, which will be the omega n squared, must be equal to k over m. So that's actually the final one. And if I again now rewrite this such that I have the k isolated, I have this expression, substitute the values, you will get 66.6 newtons per meter. So I have the necessary values for this exercise. So what I have now is the following. This transfer function will now, just substituting the values for the kdc, omega n, and also the zeta, will be this one. And if I simplify this, I will have this expression for h. If I do the same for my g, from my differential equation, also from these values, I have this expression now. And if I also simplify this, I will of course have exact same expression for my transfer function for g. So the model and also the transfer function of our system are exactly equal to each other. So let's look at the situation now in the simulation. Now the mechanical system in the Simulink will be used first, and we will use also the package Simscape to determine the response for that one. In Simscape you can generate a mechanical system like this, so you can draw a mechanical system. You can see that the step inputs force is shown here, and what we also see is there's a Simulink to physical system converter, because the Simulink signal is different than the actual physical system. So what you apply must be converted to a physical system. That's actually done here. So we convert that from the signal from the Simulink to a physical system. What you also see is, of course, in order to plot also the signal in Simulink, you need to, of course, also have the output physical system converted to Simulink, which is also shown here. Now, this is the translational damper. I will also show that later on, how you grab these elements from the Simscape in Simulink. This is the translational spring, and this is our mass here. So we have actually all the necessary elements. What you need to do is, of course, also apply a force. So that's actually the ideal force source. That's actually the ideal force source. We also need a reference like we have in electric circuits, so like a ground. So this is the mechanical reference in our translational mechanical system. So all those elements like C here are placed in the reference. What you also need to know is, of course, we would like to apply a force, but we also want to measure the displacement or the distance of that mass. So that is done using the ideal translational motion sensor. So we will measure those and we will apply this force. And then we also have a solver configuration to determine actual differential equation for this one, and also plot the required results. What you also see is the P, which is the physical output, goes here and it will convert it and it goes into the scope. So the scope has now two inputs, which is just the force input directly and also the output, which is the distance or the displacement of this force. Okay, you can see now the drawing, and we will now look at the results of this scope in the next slide. So this is the result what we have. This is the step input, which is then the 4 newtons, that's the red line, and the green line is our response. What you see is actually from here that the value here, the peak value, is 81.078 millimeters at 0.321 seconds. So that's the first one, and I see that the steady state value is 60.00 millimeters. You can also see that here in the labels. At this time, this time, I have a value of 81.078 millimeters, and here for this time approximately just a random value, then I have 60 millimeters, because this is already approaching to 60 or 0.06 meters. Okay, so the peak value is given here, and also the peak time associated with that one. So what you have, of course, from the given plot or the given graph in this exercise was the steady state value was determined as 60 millimeters. The peak time was 0.32 seconds, and our peak value, or the X max, was actually 81 millimeters. So these are very close to what we now have determined from the simulation in Simulink. So very nice result. We also did that in a different form, so using the command window in MATLAB. So just generating a very small script and then use the step command in MATLAB to determine the step response. And I also did that here, and this is what we have. You can see the transfer function again, and you can see the overshoot 35%, exactly what we have determined from the plot, given plot in this exercise. So this is all fine, and you can also see that the peak amplitude is 0.0811, very close to 80 millimeters or 8 centimeters, and also the peak time of 0.332 seconds, or very close to what we have here. What you also see is the steady state values 0.06 meters, or also very close to the 6 centimeters. So the simulation will give these results, and our calculations, or actually the determined values from the graph, were these one, and you can see these are very close to what we have now simulated. So you can see the simulation results and also the values we have determined and also what we have calculated do match very well, and also the values for the mass, the damping coefficient, also the spring constants are correct. That is actually the confirmation what we have seen here. So what we now do is we will now jump to MATLAB and see how we will generate these plots also in MATLAB. So let's jump to MATLAB. So this is the MATLAB command here. We have the command window of the MATLAB and also a script I have already prepared for you. So this is the definition of a Laplace parameter, which is shown here, and these are the system parameters we have determined actually from the plot. So this is the mass, this is the damping coefficient, we have also the spring constant. Now this is the transfer function, again just using the expression we have determined in our analysis. This is the force input, which is just 4 newtons, again shown here, and this is the response y, which is then g, the transfer function, times that input. So I will run this and I will now see what the result is in this MATLAB. So let's run this first. So run, now it is running the script, and if I now do step and I do y and then grid on, we can see what kind of plot we get. Okay, this is the plot we have. We can also see the label, that's also very important. So y is actually our response. So if I now also look at the peak response that's shown here, you can see the 35% overshoot and also the peak time and also the peak value all exact same as we have discussed and very close to what we have determined from the plot. And let's also look at the steady state value, which is very close to 6 centimeters or 0.06 meters. So this is very nice. The results are confirming the analysis from the plot. Okay, now let's look at the analysis or the mechanical system in Simulink using Simscape. So first I will type in Simscape. Here, this is actually what we have. So I have type in Simscape. This is now a building block or library with where we can find the mechanical systems, or also hydraulic system and electrical system. So we can go to utilities and also the foundation library. You can see the elements we need for our simulations. Also, I need to have a Simulink running, so I will also generate a Simulink here and then use that to determine the response. So let's also use the Simulink, and I can just open a blank model, and I can also say, okay, I already know that we want the mechanical translational system, so I can also create that one. That's also fine. So let's do just a blank model to see how we can start from scratch. Okay, this is what we have. This is the system. I will just make this smaller. Okay, we have now our blank Simulink model here, or Simulink page, and this is the library where we find our mechanical elements. So first we go to utilities, and then there's a new page opening. So we have seen here the physical system to Simulink converter. We need that one, so let's place it in here. We also need a Simulink to physical system converter, so let's also place it in here. Okay, and we also need the solver configuration, so I'll also place it in here. So those three are required from here. So this is actually for this page. We go now to foundation library, so double click on that one. Now you can see a lot of blocks here, so we have actually different regions where we can find elements like electrical and also hydraulic, etc. But we will, of course, are interested now in this example the mechanical. So we go to mechanical and also going to the translational elements. So first that one, translation elements. So we can see we have the mechanical reference, we have the spring and also the damper and also the mass. So let's first with the mass. This is the mass. I will place it a little bit to the right. I have also the reference, so I will place it here. I also have a damper, so damper is here, and I also have the spring. So all of them are here. So we have now the necessary values and elements. Okay, now let's then go back and then of course need also the source, which is the force input. So we go to the force and you can see here different forces. So ideal force source, ideal torque source, ideal translation and velocity source, etc. Of course we need this one, so I will move in this one, and I will do of course now just rotation with Control R in Windows, and I will have this. So go back. I also need to measure the displacement of this mass. So what I do is also go to mechanical sensors and then ideal translational motion sensor. That's actually what I need. So I will go in here and I will also bring this in my Simulink page. So those are the necessary elements. What we also need of course is the step input, which goes in here, and also the scope, which will of course measure our response. So for that we need to go to the library of the Simulink, and you can see in commonly used blocks that the scope is already given, but if you cannot find it, you can also go to sources. You can, the sinks, you can also see the scope here. So I will place a scope here and I go to sources and I will find also my steps. So I have now the necessary blocks for my system. So I will now make this the full screen because that's actually what we need, and I will now zoom in here, and then we can move on in this part of the page. So this is the step input. I will now connect it to this part, which is the part which is then the conversion from the physical to the from the simulation to the physical signal. This is step input, and of course we can also say that we want if you want to show also the label, you can also do this, hover on it, and then see the 3 dots, and then do show block name. Okay, this will now be connected in here. So this is the connection. This is the connection for the reference, so I will bring it here, and also want to see that. So let me also see that. So this is the connection here, so I will bring it here. This is the connection for this. Okay, this is step. Let me also show black name step, and this is of course our step input force, and that's now of course 4 newtons. But if I just say step time and then also the final value is 4, that means in the Simulink it is 4, but in a physical system it means 4 newtons. So this is the Simulink to physical signal converter. This is now the ideal force source then to convert actually that Simulink signal. This is the reference, so this is the mass. So if I now also make that visible and also connect that in here such that I have that force applied to that force. Now I will now bring this here together, and this is now the connection to the mass and also the damping coefficient and also the spring constant. Of course you can move it here to make it a little bit easy to see. Let me redraw this so these are shown in parallel. Okay, so this is the damper and this is our spring. Now let's first also fill in the value of the mass, because we already calculated that it was 0.622 kilograms, so that's also shown here. We also had a value for the damper, so that was 4.08 Newton per meter per second, and also the spring constant was calculated was as 66.6 Newton per meter. So that's what we have. Okay, what we of course need to know is the measurement of the movement of this mass. So let's also connect that here. So I will also make the connection here. This will go to this block. So this is actually the conversion from the physical to Simulink. So that's actually what I have. And this one is the connection to the mechanical reference signal, which is then actually shown here. So this goes here, and this is my output. So I will also say this is the output, so that the output input in here. Double click on that line and you can type in what you want. Okay, this is now also connected together, and that is also then now connected to the reference signal. So we have also this connected in here. Let's do that like this, like that, and then connect it in this form. Okay, so we have now the necessary elements, but for the scope I need 2 inputs. So I will go first to scope, double click on scope, and I will have view configuration properties, and I will have 2 inputs. What I also need to have is the sample time is a little bit smaller, because I want to have an accurate plot. So I will make this 0.001 to have a little bit more accurate plot. Okay, the time is okay, display This is all fine, so let's first see what we have. We also want, of course, the two plots next on top of each other. So I have the input and also the response like this. Okay, this is now for our plot. This is our scope. All right, so actually I have now the necessary elements. So let me minimize this. This is for the scope. So I have the output. What I also need is, of course, the input. So if I now also bring the input in here, this is the input. So I have now the input and also the output. So now we will generate the signal for the input and also the output response using the scope and see what we get. So the scope is in here. Let's make it larger and then run this and see what we get. So running. Okay, let's double click on the scope. You can see the plot here. This is the response and this is the input. You can see you can of course change all the colors. So let's also go to the style and then change the color, let's say a red one, and then make also a little bit thicker. So you can see it easily. So this goes to 4 at time equals to 1. Doesn't matter, of course, it was actually initially at 0. And then you can see that the yellow line is the response. Now, if I want to measure this in a little bit accurate way, you can say, okay, I will go to Tools, Measurements, and I will like to have the cursor measurements. Then you can see a trace selection at the left or right side. So you can now select the correct curve and then go to the peak value here, like let's say this one, and this is done for label 1. You can see the peak value here and also the at what time it is. It's of course starting from 1 all the way to here. So this is actually 0.32 seconds. So that's also correct. And if I now also look at the final value, it is very close to 60 millimeters. So that's also fine. So this is also again a confirmation that the system is actually very close to what we have given initially as the exercise, the plot in the first slide. So this is now also using simulation in Simulink, using Simscape, and we have determined now from the mechanical model that the system parameters are correct because the spring constant, the mass, and also the damping coefficient will produce this response. All right, guys. This is, for example, about a mechanical system, mass damper spring system, which is a translational system. We will see, of course, different examples also from different domains like electrical systems. And if you have any questions, comments, please let me know and I will try to answer them as soon as possible. Thanks again and see you next time.